Hello, I'm Julie, a PhD student at UT Austin, and I'm so excited to introduce my research paper entitled Sample Efficient Dynamics Learning for Symmetrical Light Robots, Leveraging Physics Invariance and Geometry Symmetries. Let's begin by discussing the motivation behind this paper. Light robots commonly have multiple robot states with the same physical characteristics due to their floating-based system and symmetrical structure. My research just started from a question: what if we can use this known prior for robot learning? Firstly, let me give you an example of physical invariance. As you can see, two robots in different locations can be physically equivalent if the gravity applied to the robot is the same. Second, we may want to use geometric symmetry, which is very common in the robot system. Many robots are designed to have symmetries to take advantages from their symmetrical structure to generate the balanced movement as animal does. In this paper, we specifically consider the rotation equivariance in a robot. However, vector representation is limited in its ability to capture these equivariant properties, as the data assigned to each leg is fixed in the vector representation. This can result in data and training inefficiency, as fit-for neural network must solely rely on the available data set to learn the relationship between each leg. Now, let's move on to the methods. Instead of using vector representation, we propose to use set and graph, the data structure that has interchangeable input and output. In these data structures, the order of the objects does not matter, and we use this property to consider symmetries in light robots. Along with the data structure, the permutation equivariant networks were used to deal with interchangeable objects. Leveraging symmetric functions to combine the input features, we can build the permutation equivariant layers, ensuring that the output of the layer is the same regardless of the order of the input. Typically, floating-based robot system can be represented by the robot joint configuration, along with the position and orientation of the base described using generalized coordinates. However, to fit the data in the proposed data structure and to ensure physics invariance and rotation equivariance, we instead use a leg-wise data structure consisting of a set of vectors, where each vector represents the features of the corresponding leg, such as joints, contact, and magnet activation information. Also, instead of using base configuration expressed in a fixed frame, we use body frame representation, which does not depend on the choice of the fixed frame. So for the inverse dynamics, we structure input and output as a leg-wise set, and each leg-wise input data consists of current joint state, desired joint state, base movement features expressed in a leg frame, and contact and magnet activation status of each leg. This way, we can achieve data structure permutational equivariance. And then we build two types of neural network working on the set structure and graph structure. You can find details in our paper. In the next few slides, I'll share my experiment results. To evaluate the proposed model, we first collected climbing trajectory data in a simulation environment using whole body locomotion controller. We specifically included various scenarios with rotational symmetry and different directional slopes to demonstrate the data efficiency of the proposed model. After collecting the climbing data, we generated data set from the trajectory. We then trained the proposed neural network with two other neural networks for comparison. If a model can perform well on unseen data, it indicates that it requires less training data to cover the entire domain for prediction. To this end, we compared the torque error over the entire data set when models are trained with 25%, 50%, and 75% of the data set. As shown, the proposed method exhibited superior prediction accuracy compared to other models and comparatively showed good performance when trained with smaller portion of the data. Finally, we benchmarked the performance of each model as controllers to evaluate the tracking performance when each model is used as an inverse dynamics controllers. We specifically compare when FFNN and SDGNN are used solely as inverse dynamic controllers, and additionally when FFNN is used with PD controller. You will see that the FFNN IDM controller fails to track the reference trajectory, while SDGNN IDM controller successfully tracked the given trajectory. And you'll see with feedback from a PD controller, FFNN works comparatively well, though we set the gain to be very small enough not to dominate the control, which means that the failure of FFNN IDM controller is due to its lack of generalization ability to recover from the error accumulated during control. So these are our conclusion. First, the proposed models have better generalization ability, which means that they are more sample efficient. Second, when the proposed model is used as an inverse dynamics controller, it tends to be more robust and accurate for trajectory tracking. Thank you for watching this video.